right, so let's continue now on another subject. And the one that I want to talk to you about now is pendulum. I have a pendulum, and the pendulum at time t equals 0, this angle is theta 0, and I know what that angle is. It's 5 degrees, which is approximately 0.09 radians. At that time t equals 0, I give this pendulum a tangential speed. I call it v of b, because I call this point b. It's going to arc. I call this a. So this is a circle, and it comes to a halt, let's say here, at point C. And then this angle is the maximum angle possible, is theta maximum. Let the length of the pendulum, for simplicity, simply be 1 meter. It is small angle approximation. The angles will never be very large, as you will see later when we calculate theta maximum, and so we know that we're going to get a simple harmonic oscillation to a very good approximation. So theta is going to be that angle theta maximum times the cosine, or if you want to be my guest, you can make this a sine. I always work with cosines, omega t plus phi. And omega equals the square root of g over L. I will give you some equations during your exam, but this one I will not give you. I just assume that you remember this, and that the period of the pendulum equals 2 pi times the square root of L over g. So we know omega, because we know g and we know L. And now a reasonable question is, what would be theta maximum? Well, if we knew this, then we would know what theta maximum is. Because this part here equals L times the cosine of theta max. And so this is L minus L cosine theta max. So it comes down to calculating how high this object comes above point A. Well, I will split this into two heights. This one, which I call h1, and this one, which I call h2. And so the one that we really want to know is what is h1 plus h2. Because h1 plus h2 will be L times 1 minus the cosine of theta max. And so the moment we have h1 plus h2, we immediately have the maximum angle. Now h1 is a piece of cake, because we know that point B, that this object is at B when theta 0 is 5 degrees. So h1 equals L times 1 minus the cosine of theta 0. And you know theta 0. And so you'll find then, if you're interested in numbers, but don't bother if you don't like numbers, for the numbers that I gave you, this is 0.0038 meters. It's only 3.8 millimeters. It's a teeny-weeny little bit. It's a large displacement in this direction, but very little in this direction. So we know already what h1 is. So now what is h2? Well, we could now use the conservation of mechanical energy. And we could say, let us call arbitrarily the gravitational potential energy at point A, let's call that 0. And going to apply the conservation of mechanical energy, which means that the kinetic energy at A plus the potential energy at A must be the kinetic energy at B plus the potential energy at B equals the kinetic energy at C plus the potential energy at C. Now the potential energy at A is 0, because we define it that way. The kinetic energy at C is 0 because it comes to a halt. So now we can write down that 1/2 m VA squared equals 1/2 m Vb squared plus mg times h1, that is the potential energy at point B. It's higher than this point A, vertical separation h1, and that equals the potential energy at point C, which is mg times h1 plus h2. And if you compare this part of the equation, you see that you lose mg h1, and so you'll find that m Vb squared, on to carry the 1/2 for now, we can still do that, equals mg times h2. And so you will find immediately h2 equals v of b squared, which is known. In our case, it must be a known number. I'll give you in a minute what that is. And that is divided by 2g. And this v of b that I had in mind, numbers are really not that important. You don't have a calculator anyhow at your exam. But I was going to give this a speed of 0.3 meters per second in this direction in order to keep the maximum angle quite modest. So I know h2. And now that I know h2 and I know h1, I can go to this equation and I can ask what is the cosine of theta maximum. h2, by the way, in case you're interested in numbers, is about 0.0045. So it is 4.5 millimeters. So it was originally 3.8 millimeters h1, and now h2 is 4.5 millimeters higher. So you can calculate the cosine of theta max. However, I said to myself, if we use the conservation of mechanical energy, can we not also use the work energy theorem? Why not? That should work as well. The work energy theorem tells me that the work done on that object, when the object moves from A to B, equals the kinetic energy at B minus the kinetic energy at A. That is 1/2 m Vb squared minus 1/2 m Va squared. And how much work was done by gravity in going from A to B? Because gravity is the only force that does work. The tension is not doing any work because the tension, which is in this direction, is always perpendicular to the direction of motion. And work is a dot product between force and the direction of motion, perpendicular to each other. So that's 0. So it's only mg that matters, the gravitational force. Well, when it goes from A to B, the work done by gravity is minus mg h1. Object goes up, does negative work, equals minus mg h1. Now look at that equation. And look, if you want to, here. Compare this one with this one. Completely identical. So the work energy theorem is, of course, in a way the same as the conservation of mechanical energy. The work done when the object goes from B to C is the kinetic energy at C minus the kinetic energy at B. That equals 1/2 m Vc squared minus 1/2 m Vb squared. And that is the work that gravity is doing when the object goes from B to C. And that work is minus mg h2. So this equals minus mg h2. This is 0. And so you see what you see here is exactly what you see here. The two are identical. And so you could have used the work energy theorem, or you can use the conservation of mechanical energy. That makes no difference. And so you now can calculate theta maximum. And for those of you who want some numbers, I found that theta maximum was plus or minus 7.4 degrees. You always get two angles. And in radians, that would be plus or minus 0.13 radians. You know what the cosine of the angle is, so you always get two angles. There's nothing you can do about it. And so now you can ask yourself the question, what is phi? Phi is always a bit of a pain in the neck, and there is really not all that much physics in phi. But I was sort of curious for these initial conditions what phi would be. And so let's just take a quick look at that. And so if we want to know what phi is, we have to look at the initial condition that at t equals 0, the velocity at point B is plus 0.3 in this direction. And we know that theta equals theta 0, and we know what theta 0 is. That was the 5 degrees, that is the 0.09 radians. And so I'm going to substitute that in my solution. So I know when t equals 0, I know that theta equals theta 0. So theta 0, I know what theta 0 is. We just calculated what theta max is, times the cosine of phi at t equals 0. And so out pop two angles of phi, plus and minus phi 1. You always find the plus and a minus sign because the cosine of plus the angle is the same as the cosine of minus the angle. So now we have to find out which of the two it is. By the way, when you find that theta maximum equals plus or minus 0.13 radians, you could have picked either plus or minus. I picked the plus. If you would have picked the minus, you would have found a different phase angle. But you can't pick minus. Just want to remind you that I picked the plus in whatever follows. And so now I have to take into account the fact that at t equals 0, that I know the velocity vb. And how does that come in? Well, I take the derivative of that equation there, and so I get that d theta dt, which is the angular velocity in radians per second at any moment in time, but we are going to evaluate it at t equals 0, equals minus omega theta max times the sine of omega t plus phi, but we will evaluate it at t equals 0. What is the theta dt? Well, the theta dt is v divided by L. This is v divided by L, and is therefore plus 0.3. This plus because at t equals 0, the angle is increasing. So it is plus. How do we know it's v over L? Well, remember, we discussed that before. If the pendulum changes the angle by an amount d theta, and if this arc here, I call that ds, and if the length is L, then the definition of d theta, the angle in radians, is ds divided by L. If you divide both sides by dt, which mathematicians cannot do, but physicists can, then you get d theta dt equals ds dt, and that is the velocity divided by L. So you see that d theta dt is v divided by L. And so we now have a second equation. We now can solve for sine phi. That gives you again two angles. That gives you an angle phi 2, and that gives you 180 degrees minus phi 2. They have the same value for sine phi. But only one of this will be the same as one of these. And that's the one that you pick. And in my case, for my value of plus 0.13, I find then that phi equals minus 0.82 radians. It is about minus 47 degrees. There's not much physics in the phase angle. What is interesting, perhaps, is to mention that if we had chosen the speed at time t equals 0, if we had given its speed in this direction of 0.3 meters per second, the theta maximum would not have changed. Of course not. But the phi would have changed. In fact, the phi that you would have found would have been plus 0.82. And for those of you who had preferred to use the theta maximum to take minus 0.13, they would have found a different phase angle altogether.